Hi, stat students. I miss you. I can't believe I don't get to see you again this semester. So I decided to make these videos for you. So it'll sort of be like I'm here teaching you. If you get confused or you're not sure about something, you can always text me or call me or FaceTime me or whatever it is you need to do. And we'll make sure that you get through your Wiley problems. You can email me and take pictures of whatever it is that's bothering you. So please don't hesitate to do that. I want to make sure that you all get through the class and get the grade that you want and that you feel comfortable with everything. We're going to have 3 videos. This will be our first, so it's chapter 8. Then we are also going to have chapter 9 and then a study guide for test 4. So we're going to do all of chapter 8 today, so it is going to be a little bit long. Feel free to pause or stop or continue later if you want to, but this is your assignment for the week, is just to get through chapter 8. So you're going to need 3 things. If you go to Blackboard under content, go to test 4, and you will see the blank chapter 8 packet, which is what I have right here. Then you will also see the completed chapter 8 packet, which is just my version with all of my notes on it that you're welcome to use. You're also going to see 2 more documents there. You are going to see a confidence level chart. That's what this guy is. And so it's called a confidence level chart. You're going to want that. The other item that you're going to need is called the degrees of freedom chart. And it looks like this. Sometimes it's called the T table. So you're going to hear me refer to it as the T chart or the T table, sort of like we did with the Z table, but this is the letter T instead. So 3 items that you'll need: chapter 8 packet, confidence level chart, and your T chart or the degrees of freedom chart. Okay, so let's jump right into chapter 8. So chapter 8 is all about estimation. So we have 3 definitions that sound very similar because they're all just variations of each other. The reason that we use these is because sometimes you're not able to get the true data that you need from a population. It's just not realistic to be able to take an entire population and get all of the data that you need. But you can take a small sample of that population and use the information from the sample, and we can estimate what our population parameters may be. So that's where chapter 8 comes in. So our first definition is basically what I just described, and it's estimation. It's the assignment of a single value, so maybe like X bar, to a population parameter, maybe mu, based on the value of the corresponding sample statistic. That's called estimation. Now, this value that we talked about up here, that's assigned to the population parameter based on that sample statistic, is called the estimate. And the sample statistic used to estimate a population parameter is the estimator. So I know those all sound very, very similar. 2 types of estimates are the point estimate and the interval estimate. So let's talk about a point estimate first. So a point estimate is like a stand-in or a replacement. It's the value of a sample statistic that is used to estimate a population parameter. So maybe like X bar or P hat, okay? Now, another important term is the margin of error, and that's represented with a capital E. This is a number that we're going to have to calculate. And this number, we're going to add or subtract it. We'll add and subtract it, actually. We have to do both, from the point estimate, and it's going to create an interval. Okay, so these are some point estimators that we are familiar with. We're familiar with X bar, right? That's a sample mean. The population parameter would be mu. That's the population mean. We're saying that we're going to set them equal. They're going to be the same for our calculations. If we're dealing with a proportion, we would have P hat. That would be the sample proportion regular old P would be the population proportion. We are going to set them equal. Okay, now we could also do the same with the variance or the standard deviation, but remember, if we are using samples and sampling distributions, which we are, remember that's from chapter 7, that's where we left off before spring break, then we will use the standard deviation for the sampling distribution. So remember this little formula here, okay? So sigma x bar is going to be the population standard deviation divided by the square root of the sample. Okay, we are also going to be using another version that looks really similar, which is S of x bar. If we have the sample standard deviation, we can take that divided by the square root of the sample. So we are using sampling distributions here, so we need the sampling standard deviation. So that we're going to have to take into account and make sure that we do that. Okay, now let's talk a little bit about interval estimation. An interval estimation, an interval is constructed, little interval here, around the point estimate. It's stated that this interval is likely to contain the corresponding population parameter. So what we're going to do is create an interval in interval notation, just like in college algebra, and we're going to have parentheses, and we're going to have a smaller value, comma, a larger value. We're going to get this interval by taking the point estimate, which would be like x bar, and we're going to subtract the margin of error to get the smaller value. We're going to add the margin of error to get the larger value, and it's going to create this little interval. And then what we are going to say is that we are confident. How confident? Well, that depends. Are we 95% confident? Are we 99% confident? We'll get to that part in a little bit, but we are a certain percentage confident that the actual population parameter is really inside this interval. Now, the good news is that if it isn't, that's okay too, because we're just doing the best we can with the information we have, right? But that's what we're going to be doing, is creating these intervals. So let's look at this example. This is a very simplified example because we don't really have to calculate much. We're given information, but let's say that if the mean score on test 3 was 80, okay, so that's going to be our x bar, all right, with a margin of error of 2.5, that's our E. The confidence interval would be 80 plus or minus 2.5, okay? So what we would do is take our 80 and subtract 2.5, we get 77.5. We would take our 80 and add 2.5 and get 82.5. And this would create our interval. We write the smaller, comma, the larger, and that's our answer. And we put parentheses around it. This is our interval, okay? And so we believe that the actual population mean is somewhere in this interval. Okay, that's what we did. So I'm going to write down here, just so you have it, it is likely that the population mean, that would be mu, is between 77.5 and 82.5. That's what that interval says. So this is what we're going to be doing for this chapter. Okay, well, I mentioned to you before that we want to know how confident are you that that falls into that interval. Okay, well, we actually call these intervals confidence intervals because they are constructed with regard to a specific confidence level. Okay, now the confidence level is a percentage that corresponds oops, kind of went off the screen there, a percentage that corresponds to a particular z-value. Yep, we're not done with z-values. Okay, so a confidence level, it's a percentage that corresponds to a particular z-value. All right, the level states how much confidence we have that that interval we created contains the true population parameter. So this CI, this would be just me being lazy, this would be confidence interval, is going to be your point estimate, so in this case X bar, plus or minus your margin of error. When you do that, you create an interval with a smaller value and a larger value. And this interval is based on this percentage. That's figured into E. So let's look at how these confidence levels and z-values, how are they related? How are we going to know how they correspond? Okay, well, that's what we're about to do here. So some commonly used confidence levels are 90%, 95%, and 99%, just for 3 commonly used ones. So here's what we're going to do. We're going to look at just a general way to do this. Then we're going to find the corresponding z-value for the 90%, the 95%, and the 99%. And then we're just going to give them all to you so that you can have them from here on out. So here we go. Let's just talk about generically how in general, how would we find this corresponding relationship? So first thing we're going to do, because we are dealing with a z-value, is we're going to draw a standard normal curve and put in our mean of 0. Now we know somewhere over to the right is a positive z-value, and then the same distance over to the left would be the negative z-value. So I created just a little interval right here. Okay, so the level, we're talking about the confidence level, is denoted by 1 minus alpha times 100%. Alpha is the area under the curve outside the interval that should contain the parameter. Okay, so this 1 minus alpha, that is your confidence level, he's inside here in that interval. What you have out here is alpha, because it's what's outside the curve. Okay, so since there's 2 of these, it's going to be alpha over 2 for each one. Okay, and that is in general how we're going to find the corresponding z-values. So we know the entire area under the curve is 1. We're told that there's an interval created with some z-values. 1 minus alpha is inside that interval. Alpha is the area outside the interval. But since there's 2 of those areas, we have to do alpha divided by 2. Okay? All right, so let's try this for 90% and see if we can get an actual z-value for 90%. Because what happens here is that you're given the confidence level and you have to calculate the margin of error. And one of the things needed for the margin of error is the corresponding z-value. And so, given the confidence level, you have to know the corresponding z-value. So that's why it's important. So here we go. What would be the corresponding z-value if they told you the confidence level was 90%? All right, well, let's draw our curve. We'll put in our 0. Again, we know there's going to be an interval. We don't know what z is, but we're going to put negative z, positive z, so that we get a nice little interval. Okay, we know inside this interval is 1 minus alpha. And we know the confidence level is 1 minus alpha times 100%. So if our confidence level is 90%, we divide by 100%, we get 0.90. That is what is inside here. This is 0.90. It's your confidence level divided by 100%. That means what's out here is going to be alpha divided by 2. Okay? Well, if the whole area is 1 and this is 0.90, then these two are going to add up to be 0.1. So alpha is 0.1. That means we have 0.1 over 2 here and 0.1 over 2 here. And there we go. Okay, now if we then go to our z-table, or we can always do inverse norm on our calculator, and we enter in 0.05, that's the area under the curve right here to the left, 0, 1, okay, then we will find a z-value of negative 1.64. Okay, well, always give the positive value of z when using confidence levels. So even though it's negative, we're going to change it to positive. That's our corresponding z value for 90%. So every time they tell you 90% confidence level, when you go to calculate your margin of error, you're going to use the z value 1.64. Okay, and that's how we did it. We took 90%, we divided by 100, that was the inside. We took 1 minus and got 0.10 and divided it by 2. Then we took one of those little areas and did inverse norm and we got our z. Okay, let's try it again. Okay, we don't even have to draw it. Let's just think about it. For 95% confidence level, okay, if we divide by 100%, we get 0.95. That's what would be in here is 0.95. So what would alpha be? Well, alpha is going to be 1 minus 0.95, which is 0.05. Okay, now there's two of those regions, so if we take 0.05 divided by 2, we have 0.025. That's what's over here. This is the number that we would put inside inverse norm, 0.025, comma 0, comma 1. We would get a negative z, but again, this says to make it positive, so we're going to make it positive. We get 1.96. So every time they tell us to make a 95% confidence level, we're going to use 1.96 as our z. Okay, last but not least, let's look at 99% confidence level. All right, we divide by 100%, we get 0.99. If I do 1 minus 0.99, I come up with 0.01. That's what would be both of these. If I divide the 0.01 by 2, I get 0.005. That's what I would put into inverse norm, 0.005, comma 0, comma 1. I get 2.57. Notice that as my confidence level increases, so does my z value. Okay. All right, now you don't have to go through this process every time they give you a confidence level. We're going to just give you the corresponding z-scores. But they think it's important to explain where these come from, that your z values and that idea of the standard normal never quite goes away. So we wanted to just talk about that a little. Okay, so if you have a 90% confidence level, you're going to use a z value of 1.65. Now that's strange, right? Because we just figured it's 1.64. So why are we using 1.65? Well, there's two particular confidence levels where if you figure the z value using the z-table versus the calculator, you get two different values. And Wiley, in your textbook and all of your tests, want the larger value. So even though we calculated it with the calculator and came up with this, they want us to use the larger. So that's what we're going to use. Okay, they don't normally ever ask for 91, 92, 93, or 94. So we're going straight to 95. We already found that was 1.96. Sometimes they do ask for 96%. That's going to give you a z-value of 2.05. They do sometimes like a 97%. That's a 2.17. We'll do a 98%. That's a 2.33. And last but not least is the 99%. This is the other confidence level that gives you a different z-value. So even though we calculated 2.57, we're going to use 2.58 in our calculations because that's what Wiley likes, okay? Well, it just so happens if you have that confidence level chart that I talked to you about, this is it. So I crossed out this middle value because you don't need those. That doesn't really have anything to do with anything. That's more of what these levels were here. Okay, so here are all your confidence levels. Here are the z-values. Again, we are going to use these larger values. If you use the smaller ones, you will get a different answer and it may or may not accept it. So go with those larger ones, but you'll have this, of course, on your test and use it for all of your homework and your quizzes. And then you also have it here, okay? So you don't have to find Z any longer. You're just gonna look it up. All right, so now we're ready to talk about the fact that there are 3 cases of interval estimation that we are gonna learn. You basically learned all of the overview of the interval estimation. Okay, first case, sigma is known. We're going to learn how to deal with that. Second case, sigma is unknown. Probably figured that one out. And last but not least, the third case, we're going to talk about proportions again with the P's and the Q's. So this is now what we're moving on to. Let's go to our first type, okay? Interval estimation for the mean when sigma is known. So for your homework and your quiz and your test, you're going to have to be able to identify what type of problem you're dealing with, and you're going to have these 3 types. So first type we're going to talk about, sigma is known. Okay, if you see sigma, well, then you know this is your type of problem. Okay, all right, so here we go. Interval estimation for this. Okay, so you're going to have a confidence interval and a confidence level. That's all that means. And you're going to be trying to estimate the population mean, or mu. So you're going to have X bar. You're going to do plus or minus E. And this just so happens to be E. Okay? So just like what we've been doing, but this is your formula for E. So with each case, your formula for E is a little different. So this is what we're dealing with when sigma's known, and sure enough, there's sigma right there, okay? So just a plain old X bar plus or minus E, but in this case, here's your margin of error. E is gonna be Z times sigma X bar, which we already said was sigma over the square root of n, okay? Now, when you are finding sigma X bar, you want to use 4 decimal places. You really want to go out as far as you can on that, just to make sure that you get a really good estimate, okay? All right, let's do this first example. Well, actually, let's do this page. And then we're going to break it down even a little bit simpler, okay? So first example, for a sample size n equals 25, the mean price of a book is X bar equals $145. Okay, welcome to college bookstores. All right, so the population standard deviation is known to be sigma equals 35. This is how you would identify the problem as a sigma known problem. Okay, remember, sigma is the population standard deviation. Okay, A, find a point estimate for the mean of the population mu. Well, here's your point estimate. Your point estimate is that mu and x bar are the same, and that's going to be 145. Okay, you have to be able to identify x bar, and it's going to be the same as your mu. Okay, B wants you to be able to find your margin of error. That's the goal. Okay, well, first thing it wants you to do is find sigma x bar. And remember, sigma x bar is sigma divided by the square root of n. This is that formula we used for the whole chapter 7. You use that over and over again on test 3. All right, well, here's sigma. Here's n. That's going to give you a 7. Now, we don't even have any decimal points to put out, but if there were, we would do 0.0000, you know, we would put 4 out if we had any. Okay, then we need a z value because your margin of error is z times this, which we just found. Okay, we have a 95% level. So we take our paper for 95% level, 1.96 is our z. That's what we're going to use. Okay, so 1.96. And this came from our confidence level chart. Okay. All right, so E is just going to be these two things multiplied together. Z times sigma x bar. And I get 13.72. Okay. Last but not least, C says construct a 95% confidence interval for the population mean. So all we're going to do is take x bar plus or minus E. And we have our interval. So I'm going to do 145 minus 13.72. That gives me 131.28. Okay. And then I'm going to do 145 plus 13.72. That gives me 158.72. So my final interval, my answer is going to be that smaller value, 131.28, comma the larger, 158.72. This is the answer I'm looking for. This is the 95% confidence interval that I'm looking for. So what this means is that we can be 95% sure, because that's the Z we used, that the mean price of a book will be between $131.28 and $158.72. And there we go. Okay? So, point estimate, margin of error, point estimate plus or minus margin of error, there's your interval. Let's do it again. We're going to use the same data, but now we want a 90% confidence interval, okay? What's going to change then is Z. For a 90% confidence interval, we go back to our chart. 90%, we're going to take this bigger value, 1.65. Remember that just came from the chart, okay? We're going to have a different margin of error because our Z is different, right? Okay, so we're going to have 1.65 times sigma x bar. I'm not sure what that's doing there. Okay, sigma x bar. This did not change because we kept our information. We kept sigma, we kept the sample size. So we're going to keep sigma x bar as 7. That did not change. And there's our margin of error. Okay, let's look at that for just a second. Let's compare the 90% margin of error with the 95% margin of error. This is 95%, this is 90%. Let's notice that the margin of error decreased when our confidence level decreased. Okay, can you see that? Is that all in the screen there? Let me move that over a little bit for you. So this is the margin of error from 95%. This is the margin of error for 90%. So it decreased when our confidence level decreased. Okay, so that's interesting. Okay, let's keep going. All right, next, using the margin of error, create our interval. Okay, so we're gonna have X bar, that didn't change, that's 145, plus or minus our margin of error, it's 11.55. So I'm gonna do 145 minus 11.55, always do smallest first, 145 plus 11.55, it's 156.55. This is our confidence interval. Okay, let's take a peek at that. Look at this interval versus this interval. This is a larger interval. This is a smaller interval. So let's also notice this is a smaller interval. Okay, so that's important. When your confidence level decreases, your interval size decreases. They're directly related. They're directly related. Okay, now note the true mean may or may not be in this interval, and that's okay either way. And we're going to look at a problem like that in a few minutes. Okay, so here's a Wiley question and a test question. When sigma is known, how can a researcher control the width of a confidence interval? Well, you can do that using the value of z, which depends on your confidence level, okay? Which depends on the confidence level, okay? You can also use the sample size N, okay? So let's go into a little bit more depth on that. Okay, I'm going to scoop my paper over a little bit. I'm going to write over here in the margin real quick. Okay, so what I'm saying is that a smaller confidence level gives a smaller confidence interval. They're directly related, Smaller confidence level gives a smaller confidence interval and vice versa. Directly related. Whatever one does, the other does. However, because n is in a denominator, it's going to have the opposite effect, an inverse effect. So, the larger n is going to give you a smaller confidence interval. So n is going to have the opposite effect. A smaller n gives you a larger interval. A larger n gives you a smaller interval. Okay, so two different ways that you can make it smaller. All right, and then we kind of repeated that here. Now, sometimes we talk about how ethically there are some gray areas in statistics. And so that's where this next formula comes in. So what if you wanted to control your interval and you wanted to control your margin of error? That you were under very strict orders to create the correct results. Okay, well, that's going to be where sample size comes in. So in order to get the desired margin of error, you can control your sample size. So the formula is going to be n equals z squared times sigma squared over margin of error squared. So this is going to come from the percentage, your confidence level. This is sigma, just straight population standard deviation. And here's your margin of error. And then as usual, always round up to a whole number. Even if it's 4.1, round it up to 5. Okay, always round up. All right, let's do some examples. First though, before we go on to do some examples, let's break this down a little bit. So somewhere you may want to jot down, here's some quick and dirty things to remember. When sigma is known, here's what we're going to do. Okay, well, first of all, x bar is mu, okay? First thing you're going to do, find sigma x bar, which is sigma over square root of n. This is your population standard deviation over your sample size, the square root of your sample size. Second thing, find z from your confidence level chart. Okay. 3, find your margin of error. You're going to take z times sigma x bar. Okay, remember you want 4 decimal places on that guy. Okay. And then last but not least, you're going to have x bar minus e and x bar plus e. And that's going to create an interval. And you're done. So that's what we're dealing with. Those 4 steps over and over and over. Okay? All right. So let's jump into some additional examples. Okay. Here we go. Number 1, for a population data set, sigma is 12.5. Okay, so sigma is known here. We know exactly what to do. How large a sample should be selected? Okay, so we don't know our sample size. We're going to use this formula. Okay, so that the margin of error of estimate for a 99% confidence interval for mu is 2.50. All right, folks, here is where we have to remember to read the problem. We need to identify all of our variables, and we can't just skip around and look for numbers. We have to read the words. Okay, here we go. All right, so z squared. Well, I need a z. Z comes from the percentage. So 99, I go to my chart, I take the bigger one, 2.58. There we go. Okay, sigma. I have sigma, it's right here, 12.5. Okay, here's where students get a little weird on me. They then say, oh, and look, I have mu. Mu is 2.50. Mu is not 2.50. What is 2.50? The margin of error. Read the words. So the margin of error of estimate for this is 2.50. That's what your margin of error is. Please, please, please be careful there, okay? And remember, this came from the 99% confidence level chart. That's where we came up with that. Okay, let me scoot it over so you can see it. There we go. Okay. All right, let's put these values in. Everybody is squared. So 2.58, we're going to square it, times 12.5, we're going to square it, over 2.50, we're going to square it. There we go. Okay, this comes out to be 166.41. We need a whole number and we always round up. There we go. There's our answer. Okay. All right, let's look at number 2. Okay. A bank manager wants to know the mean amount of mortgage paid per month by homeowners in the area. All right, so that's a population parameter that he wants, but he does not have the ability to get that information. So he's going to estimate it using a sample. A random sample of this many homeowners, okay, N is 114, showed that they pay an average of $1,573 per month. That is our X bar. Okay. The population standard deviation is 209. What symbol is population standard deviation? That's sigma. Again, you have to know your symbols. Okay. And we want a 99% confidence interval. This tells me that I need to go to my chart and that my Z is 2.58. There we go. Okay, so if I flip back to my little cheat sheet here for when sigma is known, okay, first thing I want to find is sigma X bar. So I'm going to use this information. Okay, so sigma X bar is sigma over the square root of n. And I'm going to go out 4 decimal places. There we go. That's going to give me exactly what I need. Okay. All right. Number 2 says find Z from the confidence level chart. Well, we already did that, so I guess we can call that step 2. Okay. All right. Step 3, find your margin of error. We want to multiply them together. Okay. So my E is going to be 2.58, that's my Z, times sigma X bar. Okay, and my margin of error comes out to be 50.50. Okay, I hope that doesn't look like it's bleeding into the bottom of that other guy. Let's see, 50.50. There we go. Okay. All right, then the very last step is X bar minus that margin of error and X bar plus that margin of error. So my confidence interval is going to be, here's my X bar, 1573 minus my margin of error, 1573 plus my margin of error. That's going to give me the smaller version, 1522.50, comma, the larger, 1623.50. And there's my answer. Ta-da. Okay. Now part B says, what if this is too wide? How can you reduce it? Okay, 2 ways. If we want to make this smaller, the interval smaller, we can make the confidence level, whoops, I don't know what I was writing, the confidence level smaller. Okay, the other thing we could do, remember sample size is the opposite, we could increase sample size. Opposite motion for the sample size, same motion for the confidence level, okay? So there we go. We want to make sure that you remember, make sure that you note as width of your confidence interval decreases, the confidence level decreases. N is the opposite. Okay, we'll just kind of make a little side note there. Okay, make a little side note there. All right, let's go through and do the next 2 examples, and then I think we'll call it a day. And then I'll do a part 2 on YouTube because I know it's getting pretty long. And then you can finish up the part 2 on Wednesday. Okay, here we go. Let's flip our page. Okay, part 3, number 3 and number 4. All right, so the standard deviation for a population is sigma. Again, now you know, sigma's known. We're going to use those steps. That's important. Okay, a random sample from this population gave a mean equal to this. Okay, that is our X bar. Determine or construct a 95% confidence interval for mu. Well, if I go to my table, 95% is 1.96. It's right off my table, okay? Assume n is 196. Okay, all right, here we go. So, first step, okay, is sigma x bar equals this. Okay, here we go. Step 1, we need sigma x bar. We're going to take sigma, 7.42 over square root of n. We're going to go out 4 decimal places, and we have sigma x bar. Okay, step 2, find z from the chart. Okay, we already did that. There it is. Okay, step 3, we're going to find our margin of error. We're going to do z times sigma x bar. So here's our z times sigma x bar. We get a margin of error of 1.04. Okay, last but not least, we create our interval. We do x minus and x plus. Okay, here we go. So we're going to take 48.37 minus our margin of error, and we're going to do 48.37 plus our margin of error. This is going to give us a nice little interval. Remember, smaller number first. Right there. Ta-da! All right. Well, last but not least, number 4. A city planner wants to estimate the average monthly water usage. He selects 40 households, which give a mean usage to be this many, I'm not even sure what M is, metric gallons, meter gallons. Why don't we just pretend that's not there? I don't know. Over a 1-month period. Okay, so from that sentence, we know we have an N of 40, and we have an X bar of 3406.80. How about that? Okay. Based on earlier data, the population standard deviation of monthly water usage is 387.30. What is the population standard deviation? Sigma. We're using these steps. That's extremely important that you know what that means. Okay, and a 97% confidence interval. We'll go to our chart. 97 gives us a z of 2.17. There we go. Okay, we're ready to begin. Okay, sigma is known. Step 1, find sigma of x bar. Okay, sigma of x bar, we're going to take sigma, we're going to divide it by the square root of n, and we're going to go out 4 decimal places. Okay, step 2, find our z. I always do that first. I don't know why. I guess because it's easy. Okay, step 3. We need the margin of error. We're going to multiply these two guys together. We're going to take 2.17 times 61.2375. We're going to get a margin of error of 132.89. And then last but not least, we're going to create our interval. We're going to take x bar minus our margin of error and x bar plus our margin of error. When we put that in our calculator, you should get 3273.91 as your smaller value and 3539.69 as your larger value. Scoot that over so you can see that a little better. And that is going to conclude part 1 of chapter 8. So this will be part 1, and I will be uploading a part 2 very soon for you. But if you can get this far, that has gotten you the general overview and how to find the confidence interval when sigma's known. And then next time we are going to start on sigma unknown, and we'll also finish with proportion. So we'll get through the rest of chapter 8 at that point. Okay, stats kids, I miss you. Get on Wiley. Make sure you're getting your homework and your quizzes done, and email me or text me or call me or ask for help if you need it. I'm here. Bye-bye.